We're working again with chapter 3, which is applications of derivatives, and we're right now plowing through all these different ways we can use the calculus to do curve sketching to get a basic idea what a graph of a function is going to look at. So today, section 5, we're going to look at limits at infinity. So we've played with the idea of limits that equal infinity. Now we're saying what happens as x approaches infinity. That's what we're talking about, the limits at infinity. We're going to use this to determine horizontal asymptotes, if any, of the graph of a function, and then determine its limits, infinite limits at infinity. Sheesh, that's a mouthful. So, again here, we're looking at functions and describing what happens as x approaches infinity. This is the concept of end behavior we talked about in your classes before calculus, your pre-calculus course. So you did some of this in pre-calculus. We did some with end behavior when we looked at polynomials in algebra 2. So we're going to kind of use what we did with limits. So we're doing some limit stuff again. Joy, right? Okay. So, for example, if we look at f of x is 3x squared over x squared plus 1. We can look at this with our table again. So we start and we make x get bigger and bigger. Let's get my pointer up. As we get bigger and bigger, we're noticing this looks like it's getting closer and closer to 3. As we're getting smaller and smaller, closer to negative infinity, it looks like we're approaching 3 again. So, yeah, I keep forgetting when I have animations in here. So, we can see this numerically by doing a table. This is always one way we can do with limits. If we graph it, this is what the graph is going to look like. And you can kind of see here, it's approaching f of x equals 3. So that's our horizontal asymptote. That's our end behavior. And you can see by this, all my x's are squared, so f of negative x equals f of x. This is symmetrical. So my limit to positive infinity, my limit to negative infinity is the same. That's one of the things you do have to consider, that just because you have a limit as you're going to positive infinity does not mean you're going to always have the same limit going to negative infinity. So we're going to have to think both sides. There's two ends. Any end behavior, there's two ends. So we can have two separate end behaviors. This is going back to a formal definition, going back to, our epsilon delta type of definitions we did in chapter 1, and I know you hated those. But what does it mean that we have a limit at infinity? That means that, again, as long as x is bigger than this value m, then the value of f of x is within epsilon, within some error of my limit. And that's what we can say. We can say, okay, the limit is L, because once I get past a certain point, I'm always within epsilon of that value. So I'm not going to make you do really much with that, but I want to give you that basic proof, that basic definition, again, that what we work with. Okay, if we do have a limit as a constant, the line y equals L is a horizontal asymptote if either the limit as x approaches infinity is L, or the limit as x approaches negative infinity is L. You notice we say a horizontal asymptote because it's possible to have two different horizontal asymptotes, one for negative infinity and one for positive infinity. So, and again, another thing to remember with that asymptote is this horizontal asymptote is based on x is bigger than this value m. So you can cross a horizontal asymptote as much as you want until x gets really big, or x gets really small, and then you're going to settle down and it will approach it asymptotically. But we're dealing with limits, so, you know, we can do the limit of a sum as a sum of the limits. We can do the limit of a product as a product of the limits. We have all those properties still hold true. We also have this nice one, that if I have a constant over x to any power, as long as r is a positive real rational number, the limit as x goes to infinity of any number over x to a positive power is going to be 0. And the same thing with negative infinity. It's going to approach 0 if we have a constant over x to a power. That's one of the things we're going to make heavy use out of. So, to look at this example, we're looking at the limit. We're approaching negative infinity. 2x minus 1 over x plus 1. First thing always when we're doing limits, we do direct substitution. Well, we're just going to look at, well, sorry, strike that. We're going to look at numerator and denominator. The limit as this goes to negative infinity is negative infinity. Bottom, as we go to negative infinity, that's negative infinity. So we get negative infinity over negative infinity, which is just as wonderful as 0 over 0. That's an indeterminate form. We need to get it in another form that doesn't give me that. And the way we're going to do it is we're going to find the highest power of x, and then we're going to divide both numerator and denominator by the highest power of x. In this case, it's just x to the first power. So 2x over x is 2, 1 over x is 1 over x, and same thing, x over x, 1 over x. And now when we look at this, the limit of 2 is going to be 2, limited of 1 over x, that's a number over x, so that's going to be 0. So we end up with 2 over 1, so we're going to get a limit is 2. So as x goes to negative infinity, this is going to approach 2. That's basically our main workhorse when we do these. So, give these a try. Pause the video, see what you can get with these. Now, you might have other rules, other ways to do this. I want you to use this process on these, just to work through, see that that works. Then we'll talk about the shortcuts that we gave you in pre-calculus. But right now I want you to work through those limits the way we worked through that last problem. Oh, let's go back to this here. So with this first one, again, you're going to get infinity over infinity. All of these, you're going to get that indeterminate form. So here our highest power is x squared. So we're going to go 4x minus 7 over x squared. And 5x squared plus 2 over x squared. That's that limit as x approaches 0, of course. The limit as x approaches infinity, not 0. 4x over x squared is going to be 4 over x. 7 over x squared. We got 5x squared over x squared is 5. 2 over x squared. Now when we do our substitution in, direct substitute infinity in, or the limit of 4 over x, 0 minus 0 over 5 plus 0 is 0 over 5 is 0. Next one, we see the highest power is x to the third. So we go the limit as x approaches infinity. 4x to the third over x to the third minus 7 over x to the third. This is the type of work I'm expecting to see on your homework for this and on the quiz over this section when we do that. So I am expecting to see a little bit of this. Yeah, understanding this idea of doing a limit and working with limits at infinity, even when we're working with these problems that you probably know the punchline here, what's going on. This is going to be 4 minus 7 over x cubed, 5 plus 2 over x cubed, and we're still doing the limit. Now we can plug in and we're going to get 4 minus 0 over 5 plus 0 equals 4/5. Last one, my highest power again is x to the third. Four x to the third over x to the third, 7 over x to the third, 5x squared over x to the third, 2 over x to the third. Gives me the limit as x approaches infinity of 4 minus 7 over x to the third over 3 over x plus 2 over x to the third. And that's going to be 4 minus 0 over 0 plus 0, which does not exist. So the limit, in this case, it does not exist. The limit as x approaches infinity. So that's just basically using those properties, those ideas on here. Which brings us to this. These are the guidelines, and we pretty much, for rational functions, we gave you this in pre-calculus. We just looked at the degrees. The degree of the numerator is less than that of the denominator. It's going to go to 0. If the degree of the numerator and denominator are equal, we take the ratio of the leading coefficients. And if the numerator is a greater degree than the denominator, then it's going to increase without bounds. So it's not going to have a horizontal asymptote. We can talk about doing a slant asymptote and use polynomial division to find out what that looks like. I'm not going to spend time with that right now. So, what happens when we get a square root? What do you think is going to happen here? Give this a try. See if you can work this out. Pause the video. I will be right back with you, and we'll work this together. So again, when I'm trying to, for the horizontal asymptote, I go on to say asymptotes. I want to take both the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. I got to look at it on both sides because they won't necessarily be the same. In this case, let's take a look. As we are working with this one, okay, sorry, I'm blanking out here all of a sudden. Limit as x approaches infinity of 3x minus 2 over the square root of 2x squared plus 1. The degree here is first degree. This is an x squared, but it's the square root of x squared, so it really is an x. So we're going to multiply top and bottom by 1 over x. Limit as x approaches infinity of 3x over x minus 2 over x divided by the square root of 2x squared plus 1 divided by x. Yeah, we got in the square root and not in the square root. So I'm going to make this x be the square root of x squared. So I got the limit as x approaches infinity of, on top here I have 3 minus 2 over x. On the bottom, I'm going to get the square root of 2x squared over x squared plus 1 over x squared. So, limit as x approaches infinity of 3 minus 2 over x divided by the square root of 2 plus 1 over x squared. So as we go to infinity, we're going to get 3 minus 0 over the square root of 2 plus 0 is going to be 3 over the square root of 2. Now, what's going to happen when we look at the negative case? If you think about this, right here, this denominator will always be positive. But if x is going to negative infinity, 3 times a negative number minus 2 is going to be negative. So as we're going to negative infinity, this is going to a negative over a positive. So this limit is actually going to equal a negative 3 over the square root of 2. You don't see that. That's one of the things that disappears when we do this process here, because we're dividing by that x over here is changing this from a negative to positive, and we're losing that information. So that's one of the things you got to pay attention to when you're looking at that and say, well, what's going on? Will that affect things? So watch out for those cases where the positive and the negative might actually be different values. So our definitions, with these ones that do not exist, that's when we say the limit equals infinity. And we did this again when we're talking about limits equaling infinity. Same thing can go on with this when we're looking at this end behavior. As I say, I'm not going to go much into, really go into the dividing out. We do get a chance to get together and talk face to face. We might spend a little time with that, but for what we're doing right now, I'm not going to spend time with that. I'm going to let you play with limits at infinity. Enjoy.